Okay, so that was up to 1989. Now we're up to 1990, and that's when the IPCC, the Intergovernmental Panel on Climate Change, published its first report. It was called the First Assessment Report, the FAR. And so the IPCC was created by the United Nations. The idea was that the UN wanted, at that point, climate science had become sort of developed enough that the UN was concerned about it, and they wanted to bring together all these top climate scientists to kind of summarize the latest and greatest scientific research to tell them both physically what's happening, how we can mitigate and adapt to it, and basically what we can do about it, in addition to basically the physical science, also adaptation and mitigation. And so they've done that every 5 to 7 years. They brought together all these top scientists from around the world, and they've produced these really big assessment reports. And so the first one was in 1990, and one of the aspects of each IPCC report is that they include projections from climate models of how much global warming we can expect to see under various different scenarios. And so in that first report in 1990, they published a prediction or a projection under various scenarios. And they ranged from like really fast fossil fuel burning to kind of business as usual to kind of if we take international action to reduce greenhouse gas emissions. They looked at all these different scenarios. And so far we've kind of been toward the middle high end of those scenarios. And so I put together a chart that you'll be able to see in the video comparing the model average. So what they do is they have basically several different climate models that are available at the time. And in each climate model, they run a bunch of different simulations. And so they'll kind of create a range, basically like an envelope of saying in this scenario, the warming will be between this much and this much. Basically on the high end, this is like the highest warming from all the models, and the low end is the lowest warming from all the model simulations. And the actual warming will be somewhere in that envelope, in that range. And so I've just plotted in my plot, I just took the average of all the model simulations and then compared it to the observations. And so that's the blue is the model projections, the average, and then the red is the observations, and they've been very close. So in the first report, the first IPCC report, their models under the most accurate scenario predicted about 0.25 degrees Celsius per decade warming, and since 1990 we've seen about 0.2 degrees Celsius per decade warming. So they were pretty close. At the time, the models slightly overestimated the ensuing warming, but still pretty close to reality. And so in that report, they have a quote that I like to read. It says, "Our judgment is that global mean surface air temperature has increased by 0.3 to 0.6 degrees Celsius over the past 100 years, as of 1990. The size of this warming is broadly consistent with predictions of climate models, but is also of the same magnitude as natural climate variability." So at that point, as of 1990, they're saying, there's been warming, we can't yet say if it's just natural variability or if humans are partially or completely responsible. Thus, the observed increase could be largely due to this natural variability. Alternatively, this variability and other human factors could have offset a still larger human-induced greenhouse warming. And human factors, as we talked about, as when we burn fossil fuels, we also have cooling effects from sulfur dioxide. So they're saying there could be like a natural cooling and there could be cooling from human sulfur emissions that could be offsetting some of the warming from human greenhouse gas emissions. So the unequivocal detection of the enhanced greenhouse effect is not likely for a decade or more. So that's as of 1990, they're saying it might be another 10 years, might even be more before we can say for sure that there is a human-caused global warming that's observable in the temperature record. So that's still pretty consistent with what Hansen and Sawyer said. They said by the year 2000, we expect to see human-caused global warming, and then 1990, the IPCC is saying about another decade, so about by the year 2000, we'll probably be able to see human-caused global warming. So then 5 years later, in 1995, they did the second assessment report from the IPCC. Again, they brought together all the latest climate models, and they ran a bunch of simulations, and they did projections of how much warming we could expect to see in these different scenarios. And so the one that was closest to reality, I've got in the blue line, and then the observations I've got in the red line. And so in this case, the model projections as of 1995, they actually decreased how much warming they expected to see. Just that's what happened with the models, how they advanced over those years. And so this time they predicted 0.14 degrees Celsius per decade warming, and we actually saw the 0.2 degrees Celsius per decade. So in 1990, they overestimated the warming. In 1995, they actually underestimated the warming. So they're kind of narrowing in on being accurate, but they're kind of bouncing around a little bit. As climate models advance and develop and as we understand different aspects of the climate better and better, models develop. And so they were getting close, but at that point they underestimated the warming a little bit. And so in this report they've got a quote that says, "Projections of future global mean temperature change and sea level rise confirm the potential for human activities to alter the Earth's climate to an extent unprecedented in human history. Many important aspects of climate change are effectively irreversible." So at this point they're basically saying climate change is starting to get risky. There could be these irreversible effects. We've talked about this, various feedbacks, like if a big ice sheet melts and goes into the ocean, that's irreversible because we can't take the water and put it back into ice on land. So there are these, basically at this point they're warning there is these potentially irreversible impacts that could be triggered if we don't start to do something to slow down global warming. And there was a really key quote in this report in 1996 that said, "The balance of evidence suggests a discernible human influence on global climate." So this is 1996, it was a little bit before 2000. There was actually, the scientist Ben Santer was kind of the key in putting this quote in here. And he decided, looking at all the evidence, he decided that as of 1995, 1996, there was a detectable human influence on the climate at that point. And he's actually said that putting that quote in there, I mean, it's not just him because this is it's basically a consensus document where all the different scientists had to agree, all the governments had to sign on to it, but he was kind of the key in putting it in there. And so he said that quote has kind of changed his life because he kind of got attacked from there on out. Basically from 1996 to present, he got attacked a whole bunch because he was kind of like the guy who was the first one to say we can detect climate change, human influence on the climate. And so he got attacked a lot for that. But so pretty much consistent with the predictions from Sawyer in 1972, from Hansen in the 1980s, and from the 1990 IPCC, all saying by the end of the century we should be able to detect human influence on the climate. As of 1996, the scientists decided yes, we can detect a human influence on climate change. Question? Sorry? Oh, the name was Ben Santer. He works at the Lawrence Livermore National Laboratories. So fast forward a few years later, 2001, IPCC published their third assessment report, TAR, T-A-R. And so again, latest and greatest climate models, they had updated a little bit over those 5 years, and so they did a bunch more simulations, and they published all these different scenarios, how much global warming we can expect to see. And in the most accurate scenario, I've got that in blue, and then the temperature observations are in red. In this case, they predicted 0.16 degrees Celsius per decade. And again, we saw about 0.2 degrees Celsius per decade, so getting close. They slightly underestimated how much global warming would happen, but they were quite close to what was actually observed. So a good quote from that report, they say, "There is new and stronger evidence that most of the warming observed over the past 50 years is attributable to human activities." So we've gone into the 21st century now, 2001, past that kind of decade that we said, or that date that the scientists anticipated that we would be able to detect human influence on the climate. And these climate scientists came together and said, yes, not only can we detect it, but we can now say, based on our climate modeling and based on our physical understanding, that most of the warming since 1950 is due to human activities. So and then 2007 was the next IPCC report. It was called the fourth assessment report, the AR4. They couldn't call it the FAR because the first assessment was the FAR, and so they had to say AR4. And so again, best climate models, brought them together. The climate models had advanced pretty fast at this point. There's a lot of research going into climate modeling and into climate science. And so they again did a bunch of climate model simulations, trying to anticipate global warming. I got them on this chart. The average is the blue line. The measured temperature is the red line. And in this case, they were really, really close to reality. They predicted about a 0.19 degrees Celsius warming in the ensuing decades, and we've actually seen a 0.2 degrees Celsius warming. So they are pretty much spot on as of 2007, fourth assessment report. They pretty much nailed how much global warming would happen.
I'm sorry, but you keep referring to charts and red dots and blue lines.
Yes, you'll be able to see them when they're recording.
Pardon?
You'll be able to see them recording. I'm kind of speaking to
Gotcha.
what you can see, yeah.
Thank you.
Yeah.
I wasn't going to do that.
Yeah.
So, in that 2000, so actually fast forward a few more years, the fifth assessment report was published in 2014. And so, in that one, they kind of updated their confidence in human-caused global warming, and they say it's extremely likely, which they define extremely likely as 95% confidence. So they're saying 95% confidence that more than half of the observed increase in global average surface temperature from 1951 to 2010 was caused by the anthropogenic increase in greenhouse gas concentrations and other anthropogenic forcings together. So this is 2014. Basically, they're saying super confidence that most of the warming since 1950 is due to human activities. And in this case, they're not just saying greenhouse gases because they're taking into account the cooling from human sulfur pollution too. They're saying even when you include that, we can say with 95% confidence that most of the warming since 1950 is due to human activities. So then I wanted to go back a bit. I wanted to go through all the IPCC reports, but then if we go back to 1998, there was another contrarian guy named Don Easterbrook. He was a geologist at Western Washington University, and he spoke a lot at these conferences that were funded by fossil fuel industry, like the Heartland Institute and other ones like the Cato Institute. These fossil fuel think tanks that they not only they'll publish contrarian reports, but they also regularly hold these conferences. And they call them climate conferences, but they kind of only invite the contrarian, skeptical scientists to them. And Don Easterbrook was one of them. He wasn't like a climate scientist, but he was a geologist, and he kind of dabbled in climate science. He kind of considered himself an expert, and so we'll flip at him that way. So in 1998, they had one of these conferences, and they invited Don Easterbrook. And to his credit, he actually made a prediction. Now, there actually haven't been very many contrarians who have made quantified predictions of how much warming or cooling would happen. You know, like all the ones we've talked about so far, except for Lindzen, and even Lindzen didn't really make a prediction. But all the ones we looked at have been mainstream climate scientists and climate models. There aren't a lot of contrarians who have said, like, the mainstream science is wrong, who have made their own specific predictions. So it's hard to test them because they don't say, oh, there's going to be X amount of cooling or there's going to be flat temperatures. Very few of them will go on the record and make a prediction. To his credit, Don Easterbrook made a prediction. And so he deserves some credit for that, and so it's worth looking at. So in 1998, what he predicted was that in the first 30 years of the 21st century, so basically 2000 to 2030, he predicted that we would see some kind of cooling. And so his prediction was based on basically expecting that the climate in the future will behave the same as the climate has in the past. And so in the past, there have been natural cycles. We talked about El Nino, other ocean cycles, these things like that. And so there have been periods with warming and cooling in the past. And so, for example, we had in the late 1800s to early 1900s, there was a little bit of a cooling. And in the mid 1900s, there was a little bit of a cooling. Very little bit, but a little bit of a cooling. And so basically he said, the climate is acting cyclically. There's these little coolings, and there's warming, and there's a little cooling, and there's warming. And so his prediction was that we're at the end of the warming as of 1998 or 2000. He said, we're at the end of the warming cycle. Now we're going to enter a natural cooling cycle. And so he actually created a chart that kind of showed these cycles. And he said, well, if the climate behaves like it did in the late 1800s, early 1900s, we'll see a dramatic cooling. If it behaves like it did in the mid 1900s, we'll just see a little bit of cooling. So he said one of those two things was going to happen. And so if you compare his predictions to reality, what actually happened was that the temperatures continued to warm after 2000. And so he's got the cooling predictions, the temperature actually went up, and so it diverges really badly from what he predicted. And so his predictions ranged from a 0.1 to 0.4 degrees Celsius per decade cooling, so negative 0.1 to negative 0.4 degrees Celsius. And what actually happened was a positive 2 degrees Celsius warming per decade. So he was quite far off from what actually happened. Again, credit to him for making a prediction, but his prediction was very wrong.
A historical geologist.
What's that?
Historical geologist rather than.
Yeah, he focused on, very distant past geology. Yes, right. So, about a decade later, 2008, there was a geophysicist named Shunichi Akasofu. So he was a geophysicist at the Arctic Research Center at the University of Alaska Fairbanks. And again, to his credit, he didn't think that mainstream climate scientists were right, and so he made his own prediction. It was kind of similar in that he said that the warming was basically the temperature change that we'd seen was a combination of ocean cycles and then what he called a natural recovery from the Little Ice Age. And so in sort of around 1600 to the mid-1800s, there was a period that we call the Little Ice Age, which is when the global temperatures dropped a little bit, like less than half of a degree Celsius from the previous years. And this was due, pretty much, the latest research said it was mostly because it was a period of particularly high volcanic activity. And we talked about in week 2, when you have high volcanic activity, there's more sulfur in the atmosphere, which reflects more sunlight, and so it causes a cooling effect. And so that just happened to be a period of time where there was high volcanic activity. There was also relatively low solar activity, and so there was a little bit of cooling. And so we call it the Little Ice Age because a big ice age is like 4 to 5 degrees Celsius cooling. The Little Ice Age was like half a degree Celsius cooling. And it was actually mostly focused in Europe too. There's a lot of focus on the fact that the River Thames used to freeze over during the Little Ice Age and people could ice skate on the River Thames. So because there was a lot of sort of pretty advanced academics in Europe at the time, there's a lot of focus on the cooling in Europe at the time. But globally, it was only about a little bit of cooling, a half degree Celsius. And so Akasofu's hypothesis was that we're just recovering from that Little Ice Age. So the problem with that hypothesis is that it's kind of like not physical, it's kind of magical thinking, because like things don't just like naturally recover. So my analogy is that it's like if I climb up to a bridge and I jump off the bridge and I fall to the ground, say it's 50 feet below, my decline in elevation you can't say it's like a natural recovery to where I used to be standing. Like, it doesn't really make very much sense. So what it is that I'm up high, and then what's causing me to fall, it's not a natural recovery, it's the force of gravity pulling me down. The Earth's force of gravity pulls me down back to the Earth's surface. So what's causing me to fall is the physical mechanism is gravity and the Earth's gravitational pull. So basically, if you compare that to Akasofu will be saying you're falling because you're just naturally recovering to what your elevation used to be. It's just not a physical argument. But that's what his argument is. We're just naturally recovering to what the temperature used to be, and then on top of that, there's ocean cycles that he put in there. And so basically, his prediction was that between the 2000s and the coming decades, pretty much based on where he thought we were in the cycles and natural recovery, he predicted pretty much flat temperatures with starting to get into a little bit of cooling. And of course what actually happened was that from the 2000s till present, temperatures have kept going up. And so basically he predicted 0.005 degrees Celsius per decade cooling. We actually saw 0.2 degrees Celsius per decade warming. So again, the actual observations and measurements of global temperatures have pretty much disproven his theory that we're just recovering and we're natural cycles and it's going to stop. It didn't stop, it kept on warming. It's actually worth pointing out, the charts I've got in here that you'll be able to see when you see the video are from my book, which was published a few years ago. I haven't had a chance to update them. But the 4 hottest years on record were 2014, 2015, 2016, 2017. 2018 this year is on pace to be the 4th hottest year on record. So once this year is over, the last 5 years will have been the 5 hottest years on record. And so not only had we kept on warming from 2000 to 2014, we've still kept on warming since then. We've had record-breaking temperatures for the past 5 years. So it's important to bear in mind that basically the observational reality is continuing to disprove these predictions of cooling or of that global warming would stop. It hasn't happened. It's kept on going. So, then in 2011, there was this guy named John McLean he calls himself a data analyst. He's not a climate scientist, but he has published 1 or 2 papers related to the El Nino cycle, which is related to climate change. It's related to the climate in any case. And so he's got a little bit of credibility because he's published a little bit in the area. And in 2011, he made what I consider the worst ever climate change prediction. And so what he did, this is around the time where he published his one paper related to the El Nino cycle. And in 2011, the ocean was building toward a pretty big La Nina event. And a La Nina event we talked about in week 2 is basically when in the Pacific Ocean near the equator, a bunch of cold water comes up toward the surface. And because there's cold water at the surface of the ocean, that cools the surface air temperatures above the ocean, and it causes a short-term cooling effect for the air temperatures that we measure. And so he saw this La Nina coming, and he had published this paper showing that La Nina has a pretty significant effect on short-term temperatures. And so in March of 2011, he made this prediction. He said, it's likely that 2011 will be the coolest year since 1956 or even earlier. And so again, credit to him for making a concrete, testable prediction. That's, kudos for making an effort. But the issue there is that so he's saying it's going to be the coolest year since 1956. 1956 was 0.84 degrees Celsius colder than 2010 was. So he's saying 2011 we're going to see more than a 0.84 degrees Celsius cooling from 2010. And if you look at the temperature data that NASA puts together, the biggest year-to-year temperature change on the entire record, which is over 130 years now, the biggest year-to-year temperature change is 0.32 degrees Celsius. So he's saying we're going to see a 0.84 degrees Celsius cooling, when the biggest to date was 0.32 degrees Celsius. So it's kind of shockingly, why would you possibly think that this is a smart prediction? But that was his prediction. I actually happened to run into him in a comments on an article in July of 2011. So at that point, half of the temperature data was in for the year, and it was obvious that we're going to see a little bit of cooling, but it wasn't going to be anywhere near, obviously, shockingly, not anywhere near his prediction. So I asked him, do you stand behind this prediction? Do you want to revise it? And he said, last time I looked, 2011 isn't over yet. And it's a bit premature to be crowing about an annual average when the year isn't yet complete. So halfway through 2011, he stuck by his prediction. He said, hey, the year's not over yet. It could still just cool down really, really fast. I'm standing behind it. So it'd be nice if you could see this chart because it's pretty remarkable. Basically, I've got the annual temperature data from the late 1800s to 2011. Just got the up and down wiggles every year, and then his prediction is basically we're going to see a big drop all of a sudden. And then what actually happened is there was a La Nina, so there was a little bit of a drop of about 0.1, a little bit more than 0.1 degrees Celsius from 2010 to 2011. But he predicted a 0.84 degrees Celsius. And so he wasn't even close, which, physically that's kind of an obvious thing because there's, like I said, most years there's not much of a change year to year, and the biggest change on the entire record is about 0.3 degrees Celsius. So basically it just goes to show that, these natural cycles, like El Nino and other ocean cycles, they have an effect year to year, and it can be pretty significant year to year, but it's not that significant. It's not going to cause this dramatic cooling from one year to the next. It's going to cause a little bit of a cooling and a warming. And for example, usually when we break a temperature record on the high end, it's because it's been amplified by a big El Nino, because the El Nino brings the warm ocean water up to the surface, and then the surface warms. And so that kind of combined with global warming, the warm El Nino, that's what boosts it up. And usually that's why we have a record year. It's because it's in an El Nino year. We never have cool records anymore, even though we have a big La Nina, because it's just offsetting a little bit of that long-term global warming. So these years, we frequently have temperature records on the high end. We never have cold record years anymore on a global scale.
Question?
Yes.
So you said that we had the hottest years on record for the last 5 years after we finished 18, but they were not each successfully higher, were they?
Right, so 2014 was the hottest year on record. I believe 2015 broke that record. I'm going to get these wrong, but not every year, 2016, 2017, I could be getting it wrong. 2017 didn't break the record. It was just the second or third hottest year on record. 2018 is going to be the fourth hottest year on record. So it's not that each year is breaking the record because we have these El Niños and La Niñas that influence year-to-year temperatures. So we're just frequently breaking records, but it's not going to happen every single year. And it hasn't happened every single year. It's just happening more and more frequently because global warming keeps pushing temperatures up. So that's the last prediction that we're going to look at today. And it's worth kind of thinking back, basically all the contrarians when we looked at, they all predicted cooling, or at least a little bit of cooling to dramatic cooling, and they were all very wrong. And all the mainstream models predicted significant warming, and they were all pretty close to reality. And so, the difference is that all the mainstream climate scientists, they're using like the most sophisticated climate models they can use, and today they're run on like the fastest supercomputers in the world. Because they are very, very complex models trying to simulate all these different factors, all the greenhouse gases in the atmosphere, and water vapor, and cloud changes, and ice changes, and the ocean, and the land. And they're trying to put all these like simulations, trying to simulate the entire Earth's climate. And so they're very, very complicated, and that's why they have to run them on supercomputers, because otherwise it would take too long for any of the simulations to run. And then you have like these guys like Akasofu and Easterbrook, who are and John McLean, who are just saying natural cycles happen in the past and they cause warming and cooling, and so we can expect to see natural cycles eventually going to cause another cooling. And so they're very, very simple models, and they have pretty comprehensively been disproven by the observations that the warming has continued in the global surface temperatures. And so the mainstream models are both more comprehensive and complex and detailed, and they've also been much more accurate than these really simple models just saying the climate of the future is going to change like the climate in the past. And the reason the climate of the future is not going to change like the climate in the past is because now we have this new effect of human putting tons and tons of greenhouse gases into the atmosphere that wasn't there in the past. And so that's what's causing the long-term global warming, and it's why these predictions that the climate is going to behave like it did in the past are being disproven by the observations. So that's the end of the lecture today, and now we're going to do questions and answers. So if you have questions, raise your hands up there. Yeah. The question was basically what groups have funded this climate modeling, and if their funding is secure for future modeling to become more and more comprehensive and accurate. So there's actually a lot of different groups who do climate modeling. NASA is a big one, but there's also just academic institutions like the University of Victoria in Canada is another big one. So there's both. It's basically when scientists who have expertise in modeling can get together and build a computer model, and then they have to get funding for that. So it's wherever they get their funding. Often it's from, in the United States, it's from the National Science Foundation, groups like that that fund scientific grants. Or internationally, they have their international versions of that. And so, fortunately, it's not all in the United States. There's a lot of international groups that do this too. And so there are government agencies, there are academic agencies funded by U.S. government agencies like the National Science Foundation, but there's also international groups who do it. And so we can expect that climate modeling will continue to develop and improve and evolve. The funding in the United States so far, it's still been okay. Like, it hasn't been eroded too much in Congress. So hopefully that will continue. There are various government agencies, their funding has been reduced, but those are usually groups like the EPA, groups that do more regulations as opposed to the groups that do scientific research. So far, their funding hasn't been cut too much. A little bit, but not too much. And then, of course, there's the international groups that aren't affected by internal politics in the United States and the funding of science here. So fortunately, it's kind of widespread, and so we can expect it to keep developing.
Yeah, on the question of the modeling, I'm very impressed by how complex these models are. And I've got two questions. One is, do groups share their model? And the second one is, where do you think certain models would go wrong, assuming there are scientists who want to get to the data but that don't?
So the question is, do scientists share their model, and where might the models be flawed or wrong?
Yeah, where do you,
So as to whether they share their models, they publish their methodology in scientific papers, and then I believe if groups want to use their models, it's possible. But for the most part, for example, the IPCC reports, they bring all the modelers together and run their models using the same scenarios. So they do try to kind of make them accessible, but for the most part, groups want to do their own model so that they can kind of test, like, based on my assumptions, and my model simulations match NASA's simulations, for example. So they like to do as many different, or groups of scientists like to do their own so they can, like, independently test, like, make their own predictions and see if they match up with other groups' predictions. So they do share, but at the same time, they try to do as many of their own model simulations as they can, models as they can. As to where they might be flawed, we're actually talking about this during the break. So for example, we've seen that their predictions about global temperatures have been accurate, and we can expect that to be accurate. And I mean, you actually don't even really need a climate model to make those predictions, because there's like physical, just equations like that say, based on the sensitivity, if you know what the sensitivity is, then you multiply it by like how much energy imbalance is caused by the greenhouse effect, and then you can just predict just from that, without using a climate model, how much temperatures will increase. But there's these complex interactions between temperature and like melting ice and, you know, releases of methane from permafrost and things like that. And it's kind of the impacts from climate change that are often hard to predict. Melting ice is a big one. For example, in previous IPCC reports, when they predicted how much sea level will rise, they just left out the sea level rise that will be caused by melting of big ice sheets, because they just felt like they had no idea how fast these ice sheets would melt, because they're like, we call it ice sheet dynamics, where it's like basically if the warming ocean melts kind of underneath the ice, then like a big ice sheet could collapse like really quickly, but we didn't at the time have like the scientific understanding of how fast that would happen, and so they basically underestimated sea level rise and said, you know, asterisk, we're leaving out these effects that we can't yet understand based on climate modeling. Now we're getting a little bit better at those sort of things, like, and over time we'll understand these ice sheet dynamics and the melting of the permafrost and things like that better and better, and those will get incorporated better and better into climate models. But that's the sort of thing, those kind of impacts and feedbacks and trigger points, those are the things that are still the most uncertain in the climate models. Also, a really tough one is understanding how clouds are going to change, because clouds both have cooling and warming effects because they are reflective, and so they reflect sunlight, but they're also composed of water, and so water vapor is a greenhouse gas, and so they both have warming and cooling effects, and it depends on the type of cloud and like the elevation of the cloud, which of those effects is bigger. And so as the planet warms, we're not sure like which types of clouds will increase and decrease, because the atmosphere is warming and, you know, changing, and so it's hard to predict like how exactly cloud cover will change. And so then it's hard to predict how that will impact temperatures. Will it amplify it by, you know, if the warming effect of clouds becomes bigger, will it amplify warming further, or will it start to, if, you know, the clouds increase and reflect more sunlight, will that have a cooling effect? So that's a really tough one. It looks like, based on the latest research, it will probably have a slight warming effect, but not very much. But that's another thing, like, just those sort of impacts and feedback effects. Those are the things that are really hard, that models are getting better and better at, but it's a difficult thing to model for the future.
Is another possible issue is the increase in forest fires and the increase in fires like in Indonesia where they're burning.
Yeah, so the question is, could the increase in forest fires be another significant thing, basically, that climate models are missing? Certainly, I mean, we expect that forest fires, as temperatures increase and as droughts get worse, forest fires will also get worse. At this point, they're responsible for like 5 to 10% of overall greenhouse gas emissions, and so it's not a huge effect, but it is a significant one. And so if they, you know, continue to get worse, that contribution will increase, you know, more and more. And so it won't be like a huge thing that climate models are missing if they're missing that. But it's potentially something that could be, you know, something that they have to try to incorporate, because it's not a huge contribution, but it is a significant one. So, yeah.
Another issue with global modeling is that the rainfall distribution is not known. It isn't just the cloud cover, but the whole issue of how water and how moisture will change in the distribution over land and ocean.
Yeah, so the point was that it's the distribution regionally of rainfall and things like that that's hard for models to predict. And yeah, models do kind of the best on like global averages, but like once you have to zoom in and try to predict regional changes, that becomes more and more difficult, because you have to get like really good resolution in your climate models, which again takes like really detailed models, and then it takes like a lot of supercomputing power to be able to like zoom in on like a little region and see how the climate is changing that. And so like, yeah, there's different modeling groups will sometimes they'll disagree. Like for example, California is a tricky one because we're not sure if like rainfall in California will increase or decrease, and like maybe in Southern California it'll decrease, and Northern California it'll increase. We're looking at kind of a difficult region to predict, and there's some disagreement about how rainfall is going to change in California specifically. So yeah, that's true. Like regional changes are particularly hard because you're like zooming in. You have to get like really good resolution in these models, which takes a lot of computing power and it takes a lot of understanding of like local changes and things like that. Yes.
I'm wondering if these models involve the values of a lot of rates and costs and so forth.
A lot of
Well, like methane from melting permafrost. I mean, there must, I can imagine there might be dozens, if not hundreds, of such constants, not all of which are very well known. And this would be a factor in the uncertainty.
yeah.
Model's conclusions. You go on to say that, you can resolve that to some extent by not really one monstrous computation, a monstrous number of monstrous computations.
Right, so the point is basically that there are a lot of different factors like the release of methane from permafrost and things like that we don't know like how fast that's going to happen. And so like all of those are individual uncertainties, and so the way you can address that is to basically run lots and lots of climate models lots and lots of times, and that kind of gives you a range of possible outcomes of influences from those different factors. And yeah, that's why like for example the IPCC, they run a whole bunch of different simulations of each model. They don't just run it once. They run it a bunch of different times because each different climate model run is kind of like it's one possible outcome of a certain scenario. But if you run it a bunch of times, you get all the possible outcomes, and it gives you a range of possible outcomes. And so that's why like I focus on the average, just because like that's kind of like the most likely. But then like it could really be any of these individual scenarios. So it could be one of the ones that's worse than the average. It could be one of the ones that's better than the average. But it's somewhere in that range. So that's why they give a range of possible outcomes, an envelope, and not just a single value. That's a good point. Yes.
So, weather models predict reasonably well, but on a shorter time frame. So how are these models constructed differently? Short-term weather model versus a climate model?
The question is, how are short-term weather models constructed differently than climate models? And I don't know very much about weather modeling, so that's a good question that I can't really answer. I mean, they're based on the same physics, but weather models are on kind of a smaller scale, both time and location. So, yeah. So basically, yeah, the weather models kind of start from initial condition based on the observations. Like, here's what the satellite shows. Here's where the air is. Here's where the air system is. Here's where like the storm system is, and they kind of model over the next 10 days or whatever. Here's how we simulate they're going to change, and they kind of do that really regularly, really quickly, every few minutes, every few seconds. They do it again. They update it.
I think, I don't know whether.
Anyway,
it takes less than 8 minutes, quite a bit less than 8 minutes for this model to update.
Yeah, so basically they're trying to model like you have a specific weather system and specific atmospheric conditions. Here's how we simulate it's going to change over the next 10 days or whatever. Whereas a climate model saying, here's the entire climate system, we've got the same atmospheric physics and things like that, but we're not looking at how it's going to change in this one little location over the next 14 days or 10 days. We're looking at how it's going to change over the global climate as a whole over the next X number of years or decades or whatever. So it's weather models, it's the same physics, but they're looking at a very small scale and a very small time frame.
What I've seen of the weather model outputs is that they all start from the same, this is what it is right now, but then they look at uncertainties and probabilities, and so the outcome is like this.
Yeah.
They run the models, I think it's 3 times a day maybe, something. The ones I've seen runs a few times a day, and then they they overlay all these different models and come up with what seems to be the central tendency, which is kind of like, it's more like a median rather than a mean, and that's mostly what the predictions are, and they've been getting the differences a lot closer, a lot lower than they had been like 5 years ago.
Yeah, so basically similar to how climate model is working, they're using different models and they're running them a bunch of different times, and then they get a range of outcomes, and that's why you get a probability. It's gonna, 80%, or actually right now it's 40% chance that it's gonna rain in Sacramento on Monday, and so that's why they're saying there's this range, and most likely it's a 40% chance. If you were like drill down into it, it's probably like a 20 to 60% chance that it's going to rain on Monday or something like that. But on average, it's just a probability, which is actually the same as what climate models are doing. They're saying, there's this 95% chance probability that it's gonna warm in this range from say 2 to 4 degrees Celsius by 2100. So it's all about probabilities and using a lot of different modeling simulations to create that range of possible outcomes. It's fun.
Maybe you're going to address this next week, but what are your thoughts about why this neutral information has evolved into such a partisan issue?
So the question is, why has this neutral subject of climate change evolved into a partisan issue? I would say, I'm not going to address this next week, but I would say that basically the problem is that at this point almost everything has become a partisan issue. Really the issue is that climate change, like the science is the science, but then what we do about it is policy. And the policy outcome, it's going to require some kind of action to reduce our greenhouse gas emissions. It's going to require some kind of government intervention to make that happen on the scale necessary, because we need to reduce them a lot and really fast. And so we can't do that just by individual actions. We need government intervention to make it happen. And so that's where there's the sticking point. Like, people wouldn't disagree with the science if the outcome was just like we don't have to do anything. And they say, oh, science is fine. It doesn't impact me. I'm not going to dispute it. But once what the science says we need to do, suddenly that is a problem for some people who don't want government regulation. They don't want carbon tax. They don't want the EPA to regulate greenhouse gas emissions because that's government regulation. Or they don't like the EPA, or for whatever reason they don't like what the necessary outcome is. And they say, okay, well, I don't want this outcome to happen. How can I dispute this outcome? And so the only way to dispute the outcome is if the science is wrong, because the science says we're creating this risk, and it's hard to say we shouldn't do anything about the risk because it's putting future generations at risk, kids, grandkids. It's putting us at risk, and so it's kind of hard to argue if the science is right, argue against the policy, because we have to do something. And so the only way to argue against the policy is to say the science is wrong. And so that's why there's this partisan divide, because there tends to be an opposition to government policy and regulation on the conservative side, whereas the liberal side generally doesn't have a problem with government regulation and things like that. And so it's not an opposition to the science per se. The science is just kind of what they use to dispute the need for the policy.
It's an attack on capitalism, it seems to me. That if you follow the science of climate change, you're going to have to take action, and certain corporations, a lot of them, lose from their profits.
So the question, or the point was that it's sort of an attack on capitalism because the industry is affected, the fossil fuel industry, it's going to impact their profits. I wouldn't necessarily say it's an attack on capitalism, because there are policy solutions within the capitalist framework that can be implemented. For example, we're going to talk about these in week 12, carbon tax, cap and trade, things like that are, you can build that within the current framework, and so keep your capitalist free market system, but still address climate change that way. But there are certainly industries, the fossil fuel industry, coal and oil, it's their product that's causing the problem, and so the only way to solve the problem is to stop using so much of their product. And so for them, it's certainly like an existential problem, unless they start to shift away from their main product, oil and gas and fossil fuels, and start to shift to a different energy source entirely, which, they're resistant to because they're making massive, massive profits on their current product. And so that is definitely the problem, that these really rich, powerful industries are the ones that are going to lose out from the solutions.
I think it's broader than that. I think it's all consumption.
The point is that it's all consumption. There is definitely truth to that, because consumption relates to energy use, relates to greenhouse gas emissions. True in transportation. At the same time, if you can get your energy and your transportation from carbon-free sources, then I think you should still address overconsumption, because that's increasing the amount of energy used. But if at least the energy comes from zero carbon sources, then you can still have significant consumption, but that consumption is being generated by zero carbon sources, so it's not contributing to climate change. The issue then is that you're requiring more. If you have overconsumption, you're requiring more energy, which is requiring you to, for example, install more and more solar panels and wind turbines and zero carbon energy sources. And so it's definitely better to be less overconsumptive and more energy efficient, which makes the problem easier to solve. But at the same time, like most of the problem can be solved if you get rid of the greenhouse gas emissions by replacing the fossil fuels with the zero energy carbon sources.
So, you mentioned the current administration take on climate change.
Mm-hmm.
And I didn't get a chance to read it carefully, Julia Epperson in the Washington Post had some sort of a statement that Trump administration now accepts climate change and a 4-degree centigrade warming by the end of the century.
Yeah.
Can you tell us what you know about that?
Yeah, so there was a Washington Post story yesterday, the day before, and it basically said there was a recent government report that accepted that we're going to have 7 degrees Fahrenheit, which is 4 degrees Celsius warming, global warming, by the end of the century, which was kind of weird coming from the Trump administration. You would think that they would deny that's going to happen. So basically this was like a National Highway Transportation Administration, I think, report where they're trying to look at the climate impact of if they decide to freeze fuel efficiency standards, which is their plan. They need to justify that from an environmental perspective and say it's not going to have a big environmental impact. So they did this environmental impact report, and actually they farmed it out to a consulting company. And so the consulting company basically modeled a certain scenario, and it was to get 4 degrees Celsius warming, it was a pretty high emissions scenario. I think that's, if we continue with current international policies, we're going to be closer to 3.5 degrees Celsius. And so they were looking at a pretty pessimistic scenario, whatever they're looking at, I don't know the details. But in the scenario they looked at, they anticipated that there would be 4 degrees Celsius warming, which is lots of fossil fuels and lots of carbon in the atmosphere. And so their argument was that if we freeze or don't freeze these American vehicle fuel efficiency standards, it's not going to cause a big change compared to that 4 degrees Celsius warming. And so it's basically like we're going to have 4 degrees Celsius whether or not we freeze these fuel efficiency standards. Therefore, who cares if we freeze fuel efficiency standards? Let's go ahead and burn more fossil fuel. So it's a very kind of fatalistic kind of view that like we're going to have lots of global warming no matter what we do. And I mean, it's also an argument you can make for like any individual policy. Like there's no one policy that's going to, like in any single country, that's going to like make a big difference in the amount of global warming we see. The way we're going to like significantly slow global warming is with lots and lots of individual policies in lots and lots of countries all around the world. And when you add those all up, all these little changes add up to a big change. But you can say any change is a little change, and so therefore we shouldn't do it. There's like a principle called tragedy of the commons this is related to, where, so for example, if you have a fishery and a bunch of different fishermen fishing from it, I mean, they can all say, I'm going to fish as much as I can, and then they deplete the resource, and there's no fish left, and then they're all screwed. But it's in each of their best interest to get as much fish as they can, and so if everybody looks out for their own best interest, what happens is that everybody gets screwed in the end. And so the smart thing to do is for them all to limit the amount of fish that they're fishing so that the resource doesn't get depleted, so that they can each rely on, in the future, still having fish there. But that requires like an agreement between all the different fishermen. Let's like not overfish this thing and just not look out for our own best interests. And so that's kind of the same principle here. Is in this report we're basically saying we're just going to look out for our own best interests. Just look at how much our fossil fuel emissions and our policies are going to impact climate change. And if we just look at that, it's like the fish that we're pulling out, it's not that many fish compared to all the fish that's there. And so we're just going to pull out as many fish as we can. And it's not going to make a big change just on its own. And so we're not going to worry about like the long-term health of this fishery or of the climate in this case. And so the way that you protect the health of the fishery or the climate is to make this international agreement between all the fishermen, all the countries, and say, look, we all need to make sure we're not putting so much greenhouse gases into the atmosphere that it's going to cause this long-term threat. And so that's going to involve, yes, every country needs to reduce its emissions by having better fuel efficiency standards, cleaner energy, better transportation, things like that. But that's not how the Trump administration is looking at it. They're looking at it as just from a national perspective. What we're doing on a global scale is not making a big difference, and so let's just not change what we're doing. So that's basically what that report was about. Do you have another question? No? Any other questions? No, actually, we're out of time. So if anybody has more questions, come see me. Thank you. So next week is Climate Mist, which is a fun one, and I really hope the system's working. I'll try to bring it back up just in case it's not working, because that's a bunch of videos. So that'll be a fun one. Come next week.